Okay, so we have the Chemistry Paper 2 Higher Combined Science Trilogy this time. Okay, alkanes and alkenes are hydrocarbons. Define the term hydrocarbon. Well, this is one of your set definitions. You need to know a hydrocarbon is a molecule. How do you know it's a molecule? Because it's a small covalent molecule because of the term hydrocarbon. It's a molecule made up of, and the word pretty much tells you, of hydrogen. Now you can say it either way around. It can be carbon or hydrogen, but I think hydrocarbon makes sense. Carbon and hydrogen, of hydrogen and carbon, sorry. But crucially, it's only. A hydrocarbon only has those two things in it. It's not officially a hydrocarbon if it has any other element in it. Then the general formula for alkanes is CnH2n plus 2. Determine the formula of the alkane. So this is where your maths comes in of, do you know what the N factor is? So if we put that as 10, H is going to be 2 times 10, and then plus 2. And again, if we do BODMAS or BIDMAS, we do it in the correct order, we multiply first. We're going to end up with C10 rather, H22. So again, that's a little bit application. It's not a specific one you have to memorize, but you have to be able to use those numbers. And here's another one of our sort of big descriptive or explanation paragraphs. Explain how crude oil is separated. It's not just describe, it's say why for certain steps, okay? So first of all, oil is heated. Okay? That's right here. Oil is heated. That's step number 1. Step number 2. Well, how long, or what temperature? We don't need to know the temperature, but we need to know it's until it vaporizes. Vaporize is a great word, but in reality, you can say boils as well. It's turning it into a gas, essentially. Okay? And then what's going to happen is it's going to travel up here and stop wherever it needs to stop. I say needs to stop because actually our third point is you can see the decreasing temperature arrow on the side here, so you can say the column is cooler at the top. And that's really important. You might think, why am I saying that if it says decreasing temperature? It tells me that already. But it's an important part that you need to show you understand. It's cooler at the top, okay, and that's very important. So that's where our decreasing temperature comes in. And then we then talk about why. This is our sort of description of what's the point of this. Well, those fractions, okay, or hydrocarbons, you can call them hydrocarbons. We tend to call them fractions because it's not a specific set hydrocarbon. It's a group of hydrocarbons of varying sort of within a group of lengths. The fractions condense. They condense because they turned into a gas up here, so they're going to turn back into a liquid. Fractions condense at different. Now we can say different boiling points, okay, or at their boiling points. We can say at different heights within the column. There's a variety of different ways to say it. That's where the column is cooler at the top is so important because it includes the temperature within that. I tend to talk about boiling points because it's a big part. Condensation is at a boiling point. So they condense at their boiling point. And that's it. It's relatively straightforward. You've got them heating at the start until it vaporizes, turns into a gas, and then the decreasing temperature. One thing we could maybe add is the gas travels up the column. So we can sort of put this here in between. So it is cooler at the top and the gas travels up the column and the fractions condense at their boiling point. Alright, balancing equation. We always love a balancing equation question. Some do, some hate it and some love it. So don't worry too much if you are in the I hate it category. But I always start with the most complex first. So we start with this. This has the most atoms in it. It's C14. So we'll do the C's first. So there's 14 carbons on this side, and there's 8 carbons in there, and there's 6 in there. Well, what is 6? What is 8 plus 3? It's 11. Oh, that means I need another 3. So if I put a big 2 here, that sorts out all of my carbons. So I'm just looking at carbons currently. Then if I look at my hydrogens, hydrogen is 30. Well, that's 18 plus 2 lots of 6 is 12. What's 18 plus 12? Oh, that's 30 already. Done. Nailed it. A lot of the time, I always say to people, if in doubt, chuck a 2 somewhere. Because a lot of the time, for very simple GCSE balancing equations, there are 2s a lot of the time. Next one, describe the test for alkenes. Again, this is a really important one. It is one that people tend to forget, and therefore it's asked quite a lot. It's asked quite a lot because people don't do very well on this question. But it's relatively straightforward. It's not technically part of your chemical analysis topic, even though it's an analyzing or giving a test for something. I always add the color. It's really important, I think, that you know what the starting color is in chemistry, because if you're talking about a color change, you need to know the starting color. So what you do is you add orange bromine water. Now I know it's always add orange iodine in biology. It's orange bromine water because it's not pure bromine. Okay, it's bromine that has dissolved a little bit in water, so therefore it's a little bit more orangey. And we can say this a few different ways, and it is crucial you don't use certain phrases. Clear is not a color. It just means you can see through it. It's transparent. So we can say goes colorless. Okay, that's not a problem. And you might say, well, colorless isn't a color either. Yeah, but I'm saying it doesn't have color, and clear doesn't mean that. So it goes colorless, or an even better word, it decolorizes. Rather than even have to write goes, it decolorizes, removes its color. Now you have to have the test before you get the mark for the result. You can't just write goes colorless to get the mark. You have to have written the chemical you've added to make it go colorless. Polypropene is made from propene. What type of substance is polypropene? Well, the poly tells us everything. We could actually say it's 2 different things, though. There's 2 different answers for this. Poly tells me it's a polymer, straight away. Okay, but the other way of looking at it is a lot of the time we look at naming things, especially when we group ionic and covalent substances together, we look at the elements involved. The polymer isn't looking at the element, it's just looking at the length of the chain, really. If we look at just the elements, it only has 2 elements, carbon and hydrogen. And we actually have a name for something that only has carbon and hydrogen in it. It's got hydrocarbon. So it's not a problem if you say hydrocarbon, because it's still correct. It is correct. Now, in theory, you can say plastic. I think that's a not great answer, if I'm being honest. Plastic is too woolly. It's not very... At this level, it's not very chemistry. It's not a very good use of that word. Even though it is technically a plastic, it is technically a plastic. Polymer is better at GCSE for this because we're talking about specific polymers, and hydrocarbon is definitely right because it's only got a carbon and hydrogen. Okay, I've flipped it around a little bit, the diagram, just so we have a bit more space, to be honest, because it says describe a method the student could use to produce valid results. Now, if we're looking at an exam question and we see valid results, for me, I have an alarm goes off my head and think variables. I need to be talking about variables, crucially control variables, and the phrase that all of my classes always know, repeat 3 times, remove anomalies, calculate a mean, is always going to be the last thing they say in every single method, because that is one way in which we get valid results. Okay, but what have we got here? So, describe a method the student could use. They've given us a diagram, but they haven't told us how to use the equipment necessarily. They've put it all together, but it's probably useful to actually use the equipment and say what it does. But I'm going to draw your attention to this. I would say this is the most important bit, because this is going to give us our independent variable and our dependent variable in some ways. The student investigated the effect of changing the particle size of calcium carbonate on the rate of reaction. So what are we changing here? Changing the particle size is nice and easy to read. So I'm going to write straight away at the top, my independent variable is particle size. I'm going to change it. Okay, now change is great. We can say change. How many different sizes? Well, we can say 3 different sizes. Why have I said 3? Why not? We like odd numbers for some insane reason. Okay, so I've now not just said that here's my independent variable, but I've actually given a number of options that we're going to use within our independent variable. We're going to have 3 different sizes. It means if I forget later on, I've already got that mark almost. I banked it. We then have a dependent variable. What are we going to measure in this? Well, we're going to measure loads of stuff, but what is the particle size actually going to affect? It's not going to affect the amount of water in that trough thing. It's not going to affect the amount of or volume of acid or anything else like that. The only thing it is going to affect is the rate of the reaction, so therefore the rate at which carbon dioxide is produced. This is my gas, carbon dioxide, and by rate we need 2 things. 2 things. We need a stopwatch and we need something to measure the gas. Oh, look at that, we've got a measuring cylinder. So we're already going to use that, okay? So we need our dependent variable. It's going to be, again, using that term, measure. Now, there are 2 ways to do this practical. It doesn't matter which way you do it. Both are equally valid. They give you slightly different. You choose which practical to do based on what you're looking for. Are you looking for how the rate of reaction changes over time, or are you looking for just the set rate at which the reaction finishes? Both are acceptable because they haven't given you any more information about that. Okay, so measure the volume of gas. Now, how do we measure that? We're going to say measuring cylinder. All right, we're just using the equipment they've given us. It's not fancy. But measure the volume of gas. Now, I'm going to do it this way, and I like using time. Rather, you could say for a set number of time or set time intervals or anything like that. Every 10 seconds is acceptable until reaction finishes. Okay, but how do I measure time? I'm going to say I'm using a stopwatch too, just in case they need to know that. Now, then we have our control variables. What am I going to keep the same? Okay, because currently I've just said what I'm changing and measuring. So now what am I going to keep the same? I'm going to measure same volume of acid. And again, how am I measuring it? I'm using a measuring cylinder. I'm going to measure the same mass of calcium carbonate. Oh, how am I doing that? Mass balance. Again, just using those pieces of equipment to show that you know how to do them, okay? What else am I going to do? Well, I'm going to have the same concentration of acid. We always go through the same sort of things. Same volume of acid, same mass of calcium carbonate, same concentration of acid. Or actually, do you know what we could also say? Because of all these factors that affect the rate of reaction, same temperature of acid too. And then I've gone through concentration, I've gone through temperature. We are changing the surface area through our particle size. So that's 3 out of 5 I've actually mentioned here. Now we actually get to our method. So step 1. Measure, in fact, I didn't say we measure the temperature using a thermometer, or we make sure using a thermometer it's the same temperature. I've said everything else already. So, measure acid. Now, how much acid? Let's say 25 centimeters cubed of acid, because they haven't told us. Okay, now, because we've already said the volume of acid, we don't have to put measuring cylinder again, and put in conical flask. Alright, number 2. We measure, and again, we're going to choose a random number. Let's say 5 grams of calcium carbonate. I've already said it's a mass balance, so I don't have to do it again. And put in conical flask. This is the big bit. Okay. Place stopper. Place stopper on top and start stopwatch. Okay, this is important, that order. You cannot start the stopwatch until you're actually sure that the gas will go into the measuring cylinder and not just out of the conical flask. That's where it's important, okay? Start our stopwatch. We then do our control variable, essentially, or rather our dependent variable. So, C dependent variable, because I've actually said it really nicely there. I'm going to measure the volume of gas every 10 seconds until the reaction finishes. And what's our most important? Repeat with different size particles 3 times, remove anomalies, and calculate the mean. Right, all of that is in there. All of that is really important for this one. Now, it is a lot. Okay, there's a lot we've got there. In reality, you can get rid of some of that. Some bits are absolutely essential. To get 6 marks, you have to have control variables. You have to. It has to be coherent, which means it has to be in the right order. If you're putting the stopper before you put the acid in, it's going to be wrong. So make sure you just think in the order, right? Put acid here, then I put the marble chips or calcium carbonate on, and then I put the stopper on and the stopwatch, and then measure the volume. There's an order to it. I've gone and told you lots of different control variables. In reality, you say one of them, and it's probably acceptable. But I've done lots because then I can use all those pieces of equipment as well to show them I know that. If I hadn't done all those control variables, I would have had to said measure 25 centimeters of acid using a measuring cylinder, measure 5 grams of calcium carbonate using a mass balance. This is acceptable. You can put it in the method. I just do it slightly separately. Okay, now we've done our method for a rate of reaction. Now we need to actually explain the effect. But it's not a surface area. This one is the effect of increasing the temperature. Be careful, because it could say decreasing the temperature. It could say any other option for any of those factors. So be careful and check which one they're asking you for. And crucially, it's saying refer to particles and collisions. If you don't refer to both of them, you are going to lose a mark. That's why it says it. Now, I'm surprised they haven't put it in bold, because they do that sometimes. So, we're going to keep it nice and simple. Increasing temperature, and I say nice and simple, because this answer is very year 7 in reality for a lot of it. Increasing temperature increases the rate of reaction. Okay, that is your description. It does not say that in the question. It says explain the effect of increasing temperature. It hasn't said it increases the rate of reaction, so that's your first mark. But now we get to the because. Why? Well, we're going to add particles for the first time. Particles have more energy. This is our year 7 bit. If I increase the temperature, particles have more energy. Everyone knows that one from year 7. Okay, well, so what? So, again, these are my explain words to show that I'm explaining. So, the frequency of collisions. Okay, we're not just saying it collides more. That's not strictly true. It's a bit like it is rate of reaction. It's how many collisions per second. And that's where the frequency bit comes in. You can't just say it does a lot, because that's not. If I gave it 2 days, it's going to do more collisions than if I gave it 10 seconds, regardless of the temperature. So it has to be that rate bit, the frequency of collisions increases. So it's not us just being pedantic, even though it feels that way, it's actually important. Okay, what is meant by catalyst? Again, part of our rates of reaction, you need to know this definition. Okay, it increases the rate of reaction. Our first point to call. Increases the rate of reaction. Nice and simple. How? Actually, we don't even care about the how at this point. We could say by providing an alternate pathway, reaction pathway which lowers the activation energy, all of those are acceptable, okay? But the other side of our catalyst we always mention is not used up in the reaction. Okay, it's not a reactant in that sense. It is not a reactant because it's not used up. It doesn't turn into a product. Okay, there is a perfect example of this, which is the next question really. What are catalysts in biological systems called? Biological systems is like the fanciest way ever of really us saying, what do we call catalysts in biology? Okay, enzymes. You will have learned about enzymes, that enzymes are not used up. A little bit of lipase goes a long way. Okay. Okay, this paper is quite crude oil heavy, to be honest. We've already explained how crude oil is separated. Now we're describing how crude oil is formed. No explanation here, just a description. So again, it's pretty much, do you know? Well, first of all, what happens first? Well, plankton die. Simple as that. Okay, plankton die. It could be, in fact, plankton is the best way to say it. Marine animals, plankton is the best one. Okay, plankton die, and they're buried in mud. Okay, for those of you who love geology, we are talking about sedimentary rocks. There are layers of mud coming on top. Okay, they were then compressed. The layers of mud are going to put pressure on them and it's going to compress them. Now all of that is absolutely fine. That is not enough for crude oil because you need this over millions of years. It's not going to work if it's over 10 years. This is why we struggle, because we're not making any crude oil fast enough for how much we're using it, because it's over millions of years. How sulfur dioxide can be produced by transport? Again, it's one of these interesting ones. Well, we talked about hydrocarbons and that they only contain hydrogen and carbon. The other bit they like is sulfur sometimes is found in fuels. So if a fuel contains sulfur, it doesn't always, not at all, a lot of the time it does, but it doesn't always. Fuel contains sulfur, okay, which is great. When the fuel is combusted, that's oxidation, the sulfur reacts with oxygen too. Not a huge surprise, to produce sulfur dioxide. Now I'm going to do something on the side because it's chemistry. Sulfur plus oxygen turns into, or produces sulfur dioxide. That's what we've described. Although all we've said is in the sulfur, this is fuel. And this is the air, obviously, for oxygen. Now, what are two problems caused by sulfur dioxide? For all of our atmospheric pollutants, which is what the very top is saying, it's atmospheric pollutants, there tend to be two problems we tend to talk about. There is a sort of global one I always talk about, an environmental one, and then there's a personal human one that we tend to talk about a lot of the time. So our global one, acid rain. Simple as that, nothing extra, acid rain. You could say a specific problem, it destroys trees through acid rain. It erodes buildings through acid rain. But you've got to talk about acid rain, because that's the important bit. And the other bit, always, we love this, respiratory problems or breathing problems. I mean, we don't love it, obviously, but it tends to be a problem of atmospheric pollutants, is they cause respiratory problems. You are allowed to say asthma. Okay, so you can say it increases the symptoms of asthma. That works as well. And then we got another atmospheric pollutant, how carbon monoxide can be produced by transport. Well, again, if we do our equation, carbon plus oxygen, that doesn't work. Let's get rid of some oxygen. Now it works. What did we do? We got rid of some oxygen. So we burn fuels exactly like with sulfur dioxide, but this time we don't need the sulfur bit because we know it. So we burn fuels. You could say burn oil or gas, natural gas, or crude oil you could say, or coal, any of those. They're all hydrocarbon based fuels, so that's fine. In limited oxygen. Okay. Now, what is this reaction called? Limited oxygen. It's called incomplete combustion. Right, this is a term you need to know, incomplete combustion. And now we get to our proper stuff, not just chuck a 2 somewhere, we've got to actually balance something. So carbon monoxide and nitrogen dioxide react, nitrogen and carbon dioxide are produced. These bits are essential. Okay, carbon monoxide and nitrogen dioxide, they expect you to know carbon monoxide is CO, and they don't expect you to know nitrogen dioxide, which is why they've written it for you. Just like they expect you to know nitrogen is a diatomic molecule, and they definitely want you to know carbon dioxide is this. Right? If you're just getting this down, is great. Okay, you get 1 mark for just writing this. The other bit is the balancing. So let's see, what is our most complicated? I'm going to go for probably our nitrogen because it's a reactant. We have 1 nitrogen here, but we have 2 on the other side, so we're going to put a 2 there straight away. Right, I've sorted my nitrogens out. That's fine, not a problem at all. Okay, I have not sorted my oxygens out, not at all. So let's see, we have 1, 2, 3, 4, 5. 5 on this side, not a nice number. Odd numbers are not nice. And we only have 2 on this side. Well, that's not going to work really, is it? 5 and a 2. Probably the best way to do it is to get one of them to be a 6, but one of them to be at least an even number along the way to make it slightly easier. So we can try some things out. We can say if that is a 2, we then have 2, we're going to have to put a 2 there. We then have 1, 2, 3, 4. So there's 4 on this side. That's not enough anyway. So that's not going to work. So I'll have to get rid of 2. Okay, if we try 3 on this side, 3 on that side, that's 6. And then we have 1, 2, 3, 4. Oh no, that's 7 on that side. That's not going to work either. Let's try 4. 4 on that side, 4 on that side. We have 8 on the products, and then we have 1, 2, 3, 4, 5, 6, 7, 8. Boom. We've got it. It's not always chucking 2s. A lot of the time it is, but this one is a more complicated one. They really wanted to mess with your heads on this one. Okay, printer ink is a mixture of chemicals. You can see this is our chromatography. Very common question or topic because it is a required practical. So explain why the red color did not move. So we're not talking about the movement this time, but it is still chromatography. It's still to do with solubility. So if it does not move, we need to say it does not move with the solvent, because if you remember, the solvent is the thing that moves. Okay, and it's an explain question, so we're going to write a because. So it's not moving because, I always do the 3 dots just to sort of remind myself this is an explanation, because red color. Now why is it not moving? If it moves, it means it's soluble. If it moves a lot, it's more soluble. If it moves a little, it's less soluble. If it doesn't move, it means it's insoluble. It doesn't dissolve at all in that solvent. Here we go. Calculate the distance moved by the solvent. Well, you need to know your calculation, which is RF equals the spot distance divided by the solvent distance. Okay. Now again, it's 4 marks. There is no way on earth it's only going to be 4, or all you have to do is 4 marks. So there's going to have to be some solving, rearrangement, and if you notice, there's 2 significant figures, so there's a fair bit we've got to do here. So if we look from our question, extract the data, we have 0.87 equals, now moved by the solvent is the bottom ones, which means we have 6.4, then we're going to divide it by the distance moved by the solvent, and then if we solve to rearrange, we end up with the solvent distance is 6.4 divided by 0.87, and that comes out to 7.356. Obviously that's not 2 significant figures. Some people struggle with that. It's not decimal places, it's significant figures, which means the answer is 7.4 centimeters. Suggest one reason why only 3 colors were visible. Well, there's actually lots of different reasons for this. It could have been two colors were insoluble. So if you think the red was insoluble, but there might be something else insoluble. So we're essentially saying, why couldn't we see more colors? Well, they must be blended with other colors or have traveled the same distance as other colors. One of which is they don't move at all, they're insoluble. That could be one. The color might not be seen at all, it might be a white spot, you can't really see that on white paper. Or they might have the same RF value. Now, you might have been taught everything has its own individual RF value. It does in different solvents. So for this solvent, they might have the same RF value, but if we changed it from water to ethanol or to acetone, their RF could be totally different. And that's why we have to use different solvents sometimes. So it's not just same RF value in this solvent. That's the important bit, okay? Because they don't always have the same RF value, but in certain solvents they might. Suggest how the student could use chromatography. This is where this bit comes in. Use a different solvent. Okay, it's an important aspect of chromatography, and it's a required practical because it is actually a technique we use a lot when we go higher up and analyze things at a higher level, at degree level and higher. So it's really important you know about solvents and using different solvents within chromatography. Okay, we have lots, but the most important thing for this whole bit is where it says reversible reaction. Okay, that for me tells me we're going to be talking about equilibrium, we're going to be talking about reversible reactions, obviously. And then when it says the Ford's reaction releases energy, well, for me, what type of reaction releases energy? That's an exothermic. So what I do, I always tend to label them. Exo is forwards, endo is backwards. That's important because that's the important bit to remember, and if you write it straight on your equation, it makes it easier to remember. Okay? Now, when we get to the question, it says, what is the amount of energy transferred during the reverse? Well, we've written exo, which means we know the reverse reaction is endothermic, and that's important because at least then we know that. But actually, the amount of energy released or transferred, as it's saying, in the Ford's reaction is 198, which means the amount of energy transferred in the backwards reaction is also exactly 198. There's not more or less energy needed, it is exactly the same quantity of energy. Okay, I've put the equation here as well for the next couple of questions because you need this equation. And it says the concentration of oxygen is increased. What is the effect of the position of the equilibrium? So this is where it's important. If we are making more oxygen, it is going to want to get rid of that extra oxygen, and it's going to want to go that way. So the equilibrium will shift to the right. So essentially, if we increase the oxygen or the concentration of oxygen, it will try and reduce the concentration of oxygen, which means it has to go to the right-hand side. Now I'm going to delete those arrows because the next question is the pressure was decreased. What is the effect? Well, if we add up the molecules, there's two of these and there's one of these. So adding up those molecules, there's 3 molecules on this side and there's only 2 molecules on this side. So if we decrease the pressure, it's going to want to increase the pressure. The way to increase the pressure is to move to the side where there are more molecules, and therefore the equilibrium is going to go or shift to the left. The temperature is increased. Now, if you remember, we wrote on it before, and this is why I've written it again. Exo is forwards, endo is backwards, or endothermic. What is the effect if the temperature is increased? Well, exothermic is going to increase the temperature anyway. So if we increase the temperature, it's going to want to reduce the temperature, which means the endothermic reaction will take place, which means the equilibrium will shift to the left. It's sort of getting into the habit of it always going to do the opposite of what we want. Now, a catalyst is used in the reaction. Now, this is important because this is the only one that's a little bit different. Okay, equilibrium does not change. And it's one of those sort of facts you need to know. Equilibrium does not change, and the reason why the equilibrium does not change is the rate of the forwards reaction and the backwards reaction, they both increase because that's sort of the point of a catalyst. It increases the rate of reaction. But at the rate of the forward reaction and backward reactions increase equally. So it's not that the forward increases more than the backward or vice versa. They both increase just equally. Determine the time taken for the reaction to reach equilibrium. Now this is important. Equilibrium is that point at which, although reactions are happening, the number of moles, or the concentration of products and reactants, are going to be static to a certain extent. They're not going to change massively. So we need to find a time. Well, if we look at this graph, the only place where they all, in my beautiful drawing, become horizontal, which is when the rate of reaction, for a lot of times we say the reaction's finished, but for this one it's more a case of it's reached equilibrium, is 210 seconds. You've got a range between 205 and 210. It's when it goes horizontal, okay? And what does equilibrium mean, essentially? That's what they're asking us. And it's the rate of the forwards equals rate of the backwards reaction. Simple as that. Okay, now I've missed a bit because we know it's 210. How did we know it was 210? Because the line becomes horizontal, which is what I said, I just didn't write it down. So we know it's that because the line becomes horizontal. What does the horizontal line mean? The rate of the forwards reaction equals the rate of the backwards reaction. And then we have a different graph just for sulfur trioxide. And now this is really important because it says determine the rate of reaction at 60 seconds. It's not the mean rate of reaction, it is at exactly 60 seconds. So if we go up to 60, I'm doing a beautiful thing called a tangent. I love a good tangent. Everyone loves a good tangent. And then we draw a triangle. It should obviously be drawn with a ruler at exactly 60 seconds. And then we then have to work out what's the value. Well, I think with my beautiful drawing, we're going to have 10 take away 1.8 from my y-axis. And then we're going to have 100 and probably 100. I'm going to say with my beautiful drawing 180. Take away 0 with my x-axis. Okay, so that's going to be 8.2. Divided by 180, and that's going to be our value. Simple as that. Okay, now you're saying, well, I didn't get those exact values, and you're totally right. Okay, this is what's good about a tangent, is you're allowed a lot of leeway, essentially. Okay, so if I do 8.2 on my calculator, I'm going to have this beautiful number of 0.46 moles, because actually the number is 0.4. No, it's not. In fact, I hope I could read a calculator. It's going to be 0.0455555 which means it's going to be 0.046 moles per second. Okay, so it's change in y over change in x. The tangent is where it says 60 seconds. It's giving you a precise time, not this generalized, or what's the mean rate for the first 20 seconds. A specific time tells you you're going to draw a tangent. Okay, we're on to our last question now. Give one disadvantage of using distillation. Now, you'll have learned about distillation, you'll have learned about potable water, all things of these. The big underlying aspect in the background is economics. So a disadvantage of using distillation is large amounts of energy, because you're having to boil the water and then condense the water. So large amounts of energy required. Okay. Same from when we talk about electrolysis. Why don't we always do electrolysis? Lots of energy is required. Okay. Then when it says describe another method to produce potable water, but crucially from seawater, this is where it's important. It's reverse osmosis. That's the sort of the phrase. Okay, rather than desalination, we talk about reverse osmosis, but also it's using membranes. It's not just, well, you know osmosis from biology. there needs to be a semi-permeable membrane, and so it's just being aware that when we talk about osmosis, there has to be a membrane involved. It's not just diffusion. So therefore we have to say using a membrane as well. Then we have 6.3, explain how repeating steps 4 and 5 would improve this method. Well, step 4 is heat the evaporating basin. Step 5 is weigh the evaporating basin and contents. So what we're going to be doing is, the whole point of this is we need to heat until the mass is constant. That tells us all the water is evaporated. So really, why is this important? Well, until the mass, I need to put heat in it. Heat until the mass is constant. So this is our explain bit. All the water has evaporated. Like every single required practical, there are certain aspects where, well, for every single one, explaining why do you do a method. It's not I've memorized the method, it's what's the purpose of each of these steps. And it's just asking you what is the purpose of steps 4 and 5. And we need to heat, make sure the water's gone. How do we know all of the water is evaporated? We heat until the mass is constant. Okay, calculate the mass of sodium chloride dissolved in 100 centimeters cubed. Important, first of all, is what are the units at the end? Well, they're grams. And we got 100 centimeters, so it's not too bad. Okay, but if we have 78%, well, we need to divide that by 100 straight away. Okay, that's going to give us, rather than a percentage, it's going to make it much easier. And then we're going to times it by the mass, the total mass, which was 3.5. And if we do that, we're going to get a mass of sodium chloride of 2.72 grams. So that percentage bit, we get rid of it by doing that. Well, not really, even the 100 is the sample of seawater. Okay, give two methods that can be used to extract copper from these leachate solutions. Now, this is interesting because it's all about, we're doing bacteria this time. We're doing bacteria. So there are two methods you need to know, phytomining and bioleaching. I always remember bioleaching because it makes leachate, and that's bioleaching is bacteria making leachate. That's how I remember all those words linked together. Well, how do we get rid, or how do we rather extract the copper from the solution? Well, we've got our standard method, which is very expensive, electrolysis. But if we don't want to do that, we can also do one that's slightly cheaper, we displace. So it's the displacement using iron. So we chuck a block of iron in, and all the copper will precipitate out, and the iron will replace or displace the copper from the solution. And 6.6, we have, oh, here we go, phytomining. We've done bioleaching, we're now going to do phytomining. How are the metal compounds obtained? This is your starting point. Well, we harvest the plants. So we let the plants grow. We then harvest them, or dig them up. We then burn them. And what do? Burn, really, I suppose it's one step really, but even though it's 3 marks. Burn to produce ash. And that ash has the metal compounds in it. 6.7, our very final question. Okay, we have, give your answer in meters squared, but determine the area required to produce 750 kilograms of nickel if 1 hectare of plants produces 215 kilograms of nickel. Okay, so what we've got to do is if we do 750 kilograms divided by 215, that is going to give us how many hectares we need. 3.49 hectares. Okay, but we need to give the answer in meters squared, not in hectares. But we know 1 hectare is 10,000. So what we're going to do is 3.49 times by 10,000. Easy maths in the grand scheme of things. It's going to be 34,900 meters squared. So it's working out this number, the number of hectares is that hard bit. And then once you got how many hectares there are, is this then just 10 times by 10,000.